In this work, we present Understanding Robustness Lottery, a geometric comparative visual analysis of neural network pruning approach. The success of the machine learning benefits a lot from large and deep neural network models. However, the size of the model and the computation cost became an important concern. For example, the size of GPT-7 requires 175 billion parameters and total 800 GB to store the model. Model pruning is a classical approach to compress the neural network models and reduce a model's computation costs. It selectively deletes weights, neurons, or channels of a neural network model without hurting the performance of the model. Previous research has shown that the size of a neural network model can reduce to 1 or 2 order of magnitudes without losing model's performance. Such a technique is important for deploying models in devices such as drones, autopilots, and cell phones. Furthermore, recent research has found that network pruning can not only reduce the size of the model, but also improve the model's performance and its generalization ability. In a recent robustness benchmark, network pruning approach improve a model's performance and achieve a state-of-art performance in data corruption evaluation. However, what makes a small model more efficient and robust is an interesting and important topic. Researchers often use model accuracy and different evaluation benchmarks to understand a model's behaviors. This information is valuable but not sufficient to help review enough detail of the difference between these two models. Instead, in this work, we compare models' latent feature representation of these models and observe the difference over model prunings and input corruption operations. Specifically, we compare the geometry update of this latent feature representation over this operation. The geometry of neural network feature representation is heavily shaped by the loss function used to train the neural network. For a convolution neural network, if we change the last feature encoding layer into 2 neurons and use the same loss function to train the model with different data, the output feature representation will end up with the similar geometric shapes. If we add an additional constraint in the cross-entropy loss, which forces the same class sample feature representation class together, then the geometry of the feature representation looks like a Voronoi diagram. In this work, our comparison mainly focuses on feature representation of last feature encoding layer with cross-entropy loss. We define geometric concepts, class direction, angle, margin, and error tolerance to describe each feature representation. We evaluate a model's robustness. 2 common input perturbations include noise, blur, weather, and digital perturbation, and understanding their impact on the geometry of model's feature representation. This image corruption does not change the semantic of image, and humans have no trouble to recognize these images. In this work, we design multiple view and link this view together to address domain tasks, which include evaluation table view, local geometry view, global geometry view, and geometric feature attribution view. To summarize the effect of pruning techniques and input perturbations, we designed evaluation view to summarize their impact on different CNN architectures. It contains performance evaluation summaries. The x-axis represent different corruption evaluation benchmark, and the y-axis represent different CNN architecture and pruning methods. Furthermore, domain expert can use the performance similarity view to compare the performance similarity between models over different corruption benchmarks. Local geometry views display a model's geometric feature distribution over each prediction categories. User can use it to check how pruning operation and input perturbation change each sample's feature representation. In this view, we provide trajectory, geometric, and distribution comparisons for domain expert to explore the difference. A global geometry view displays a global view of a model's feature representation's geometric properties. A sample with a small angle with a specific class direction is more likely to belong to this class. If a sample has a small angle with both class direction, then the model may be confused with both class. Here, we use filter operation of the visualization to select dog samples with high prediction probability, but actually confused with cat category. We can also display the visualization side by side between 2 models' feature representation. We can tell that above model have a better feature representation than the model below from a geometric perspective. The last view is the geometric feature attribution view. User can use the visualization to explore how input features are correlated with the geometric features. For example, the margin feature often represents robustness in model prediction. The geometric feature with respect to the margin highlight the features that are important for the robustness prediction. Here we demonstrate a use case of how do samples geometry across model correlate with network pruning and data corruption. From local geometric views, we can select samples with small angles and large L2 and observe these samples' behavior from evaluation table view. Overall, the sample with small angle and large L2 are more resilient to data corruption and model pruning. If a model has been pruned and retrained, we can see that the retrained model gained original accuracy. However, the geometry of the feature representation changed. The angle recovered to original distribution, but the L2 and margin will become significantly larger than the original model. Here we demonstrate another use case that shows the geometric difference between the robustness and PTS prune model and the regular dense and retrained model. Here, the top global geometry view is a regular model's feature representations, and the bottom is the same data but with the JPEG corruptions feature representation. We perform the same comparison on a model pruned and retrained, which will recover to the original accuracy. Its geometric feature representation is similar to the original model. The last one is the model with MPTS pruning, but lead to state-of-art data corruption robustness, and the visualization shows significant geometric difference with previous model. Besides the use case demonstration and domain expert feedback, we also perform quantitative evaluation to measure the correlation between geometric feature and sample's resiliency to data corruptions. From the evaluation result, we show that these geometric features such as angle and margin have strong correlation with the sample's resiliency. Furthermore, we also perform quantitative evaluation to measure the correlation between the geometric feature and the sample's resiliency to magnetic pruning. From the evaluation result, we show that these geometric angles and margin also have strong correlation with the impact of magnitude pruning. At the end, we conclude our presentation with the main contribution of this work.